Okay, so hello everyone, I'm Sachin, and today we'll be continuing our studies on deriving the analytical expressions for the third order nonlinear optical response functions under the second order cumulative approximation or expansion framework. In the previous lecture, we used the second order cumulative approximation framework to derive the complete analytical expression for the first order linear response function, which is essentially the theory which is required to describe uh, linear spectroscopic experiments where there is one light field which is not of too high intensity, but it's of a decent intensity that it can still be classified as a linear experiment. And then we calculated the response of the matter system to that single light field, and that was your linear response theory. So today we'll be deriving the analytical expressions for the corresponding third order experiments like pump probe spectroscopy or two-dimensional electronic spectroscopy. And in the previous lecture, could be other forms of 2D spectroscopy too. So to be more generic, we can just say 2D optical spectroscopy. But in our class, the way we are defining the density operator and the way we are doing our calculations, it's more restricted towards electronic spectroscopy, but it's generic enough to be extrapolated to other forms of 2D spectroscopy. So let's just recall how the third order nonlinear optical response functions look like. So it's R3 as a function of T1, T2, and T3. So just a recall, T1 is the interpulse delay between the two pump pulses. If you would consider a 2D experiment, but in pump probe, T1 is 0. So for pump probe experiments, you just set T1 to 0. But if you consider like two-dimensional spectroscopy experiments, T1 is not 0 and is the interpulse delay between the first two pump pulses. So if you consider a cartoon here where you have a cuvette and you have your pump pulses, so this is your first pump pulse, this is your second pump pulse, and let's just say this is your probe, right? So this is T1 and this is the delay between your first two pump pulses, and for the cartoon's sake, this is T2, which is the delay between the second pump pulse and the probe pulse, and then the T3 delay would be the time between the generated signal field, which contains your third order response essentially. I'll call it SF for signal field, and probe pulse, because I had previously discussed that the three incident light fields generate the third order response, and that signal field is emitted, and the time delay between the emitted signal field and the probe pulse is T3. So just wanted to quickly recap. And for pump probe experiments where you don't have this two-dimensional resolution. So in 2D experiments, your data is plotted as a function of two frequencies, one of an excitation frequency, call it omega 1, and one of a detection frequency, call it omega 3. So you get this two-dimensional correlation plot in two-dimensional spectroscopy, and omega 1 corresponds to the excitation frequency and omega 3 corresponds to the detection frequency. And then omega 1, this axis and this 2D plot as a function of omega 1. So let's just call the 2D plot. So whatever spectral features you observe in your 2D spectrum, let's call it S2D, omega 1, T2, omega 3, right? So this is your excitation, detection, and this is your delay between your second pump pulse and your probe pulse. So let us call your 2D spectrum this way. And this omega 1 is generated by essentially Fourier transforming your 2D signal over T1, and then this omega 3 or this detection frequency axis is generated by Fourier transforming your 2D signal, your time domain 2D signal over T3. So what I'm trying to say, this is very simplistic. So, but for our consideration here, let's just go ahead with it. There's a lot of data processing and phase cycling and so on and so forth, which we should not discuss here. But Let's just say you have your time domain 2D signal, which is T1, T2, and T3. This S2D as a function of T1, T2, and T3, which, if you recall in the previous classes I'd mentioned, is just your third order polarization signal as a function of T1, T2, and T3. And then this third order polarization signal is your 2D spectrum. And then you Fourier transform it over T1 and then T3. And then you obtain your 2D correlation plot, which is can be your 2D electronic spectrum, 2D vibrational spectrum. And it correlates, these spectral features can be thought of as correlating excitation frequencies to uh, detection frequencies. So that's good. And so today we're going to derive this third order response function. And we have already arrived at the basic structure of the third order nonlinear optical response function. So it can be written in terms of four-point dipole correlation functions. And there's a I over h bar cube here. Sum from n equal to 1 to 4. And then you have your Rn, T1, T2, T3, and then you have your Rn star. I'm sorry, I feel like this was P3T, not T1, T2, and T3. So this was a third order polarization signal calculated as a function of T. And of course, within its structure is embedded T1, T2, and T3. But if you remember our derivations and our notations, we denote it by the third order macroscopic polarization as a function of T. Of course, it does contain T1, T2, and T3 within it, but we won't digress too much into this. So the way you can think about it is your third order nonlinear response function can be derived as a summation of four subfunctions, which we are also going to call the response functions, but yes, and then this third order nonlinear optical response function is then integrated over, or I wouldn't say integrate, but a convolution is taken with three electric field strengths, and that gives you your polarization, and then a Fourier transform of your polarization over T1 and T3 gives you your 2D signal as a function of excitation and detection frequencies, and as a function of the delay time between your second pump pulse and your probe pulse. And that delay time is scanned to essentially study dynamic processes within your system. So this is just a brief overview. So certain points to remember before we proceed with our calculation is that your light matter interaction Hamiltonian, as I previously discussed, is just minus mu times E of t. So we do not consider the vectorial component of the dipole operator along with the electric field vector polarized in specific direction. So we don't consider that. And one moment, mu t. That, so we don't consider that. And for this specific calculation, we are considering a simple two-level system with a ground state and an excited electronic state. So the Hamiltonian, which is written as, so this is your matter system Hamiltonian. So your total Hamiltonian consists of your matter system as well as your light matter interaction Hamiltonian, which is given by minus mu times E of t. Mu hat. I apologize because the dipole operator is an operator, and it is, and we, this is the semi-classical treatment of the light matter interaction, as we had previously discussed. Why is it semi-classical? Because the electric fields are treated as classical number fields, and your dipole operators are treated as quantum mechanical operators. And then your matter system, your H0, has a system component, a bath component, and a system bath interaction or coupling component. And as we had previously discussed from the previous lecture, that for the two level system, the system component or the system Hamiltonian has only one term, which is h bar omega Eg. So this is written with reference to the ground state energy. So the ground state energy is assumed to be zero, and then the excited state energy is written with reference to the ground state energy. And likewise, the system bath coupling, it only contains diagonal terms, and this one diagonal term encodes the fluctuation in transition energy of this two level system. So if its average transition energy is h bar omega Eg, at some arbitrary time, this omega EGT will just be equal to omega EG, which would be your, let's just say, your average transition energy mentioned here, plus your fluctuation in transition energy at that specific time divided by h bar. So that means that this is just your fluctuating transition frequency component, right, at some arbitrary time. And then this is your average transition energy. So your system component or your system Hamiltonian includes this is the average transition energy of the two level system. So this is your dynamic transition frequency, which is given by your average transition frequency, plus some fluctuation in transition frequency, which is mediated by the coupling of your system to your path. So just to clarify all of these notations. So along with this, as we had previously discussed, the Hamiltonian of the ground state, just be very careful here because I am using capital G. So capital G implies that it's the ground electronic state plus the the vibrational manifold. Not, I wouldn't say vibrational, as we will discuss later on that the bath is often treated as vibrations, but I shouldn't use this word right now. So along with the bath states, so Hg is the Hamiltonian of the full ground state, which includes the ground electronic state in the case of two-dimensional electronic spectroscopy experiments, or if it's like two-dimensional vibrational spectroscopy experiment, it would be the ground vibrational state plus the state of the bath, which the ground state, ground electronic or vibrational state is coupled to. And as is quite evident by observing this, that the Hamiltonian of the ground state is just the bath Hamiltonian, which implies that the time evolution operator of the ground state, the complete ground state, just to repeat, Hg hat t, which you can denote using, which we have denoted in the past as u g, but I wouldn't prefer using this sort of notation because it will get confusing later on with the energy gap operator. So this is a bit of a notational issue where previously we were using u for the time evolution operator from t naught to t, let's say, and now we're using the same u for the energy gap operator. So whenever I want to consider time traversal or evolving states in time using these time evolution operators, I won't use U henceforth. So U is purely reserved for your energy gap operators. So your time evolution of your ground state is just given by exponential minus I over h bar h b t. And then this bath and system components, as we had previously discussed, they're just constant over time. So that's good. Now, let us consider the Hamiltonian of your excited state. and that is given by h bar omega Eg plus the bath, and you have the fluctuation in transition energy of the excited state, which is given by u hat Eg. So in this case, you treat the fluctuation in transition energy of the excited state in an interaction picture because this fluctuates in time as a consequence of the system bath coupling. It fluctuates in time, and if you recall, the way we define this is it is called the energy gap operator, and it essentially reports on uh, the changed transition frequency. Essentially, it reports on the fluctuations in transition frequency. So, if you have a particular two-level system, and then this is your average transition energy, then this energy gap operator at some arbitrary time, just call it t, would be reporting on its actual dynamic transition frequency. So that's what this does. And its time dependence is incurred in the interaction picture. So in this case, when you write the time evolution operator of the excited state Hamiltonian, you get e raised to the power minus I omega EGT, e raised to the power, let me just use that, exponential minus I over h bar HBT, and then you have your last term, which is positive time ordered exponential minus I over h bar 0 to t u hat eg tau t tau. Now, some things to be careful of. This is a positive time ordered exponential. So let's quickly go over this. So this positive time ordered exponential, if expanded, would look something like this. So you have the identity operator, or essentially a unity, essentially a matrix which is just ones along the diagonal and then zero everywhere else. And this causes this doesn't do anything. It just acts on a state and makes sure that the state is invariant as we discussed, plus n equal to 1 to infinity. I'm writing the full expression here, and then you have the minus I over h bar to the power n, and then an n-fold integral, or if n goes to infinity, an infinite integral, but here we write it as an n-fold integral from 0 to t tau n, 0 to tau n, d tau n minus 1, then finally from 0 to tau 2, d tau 1, and then you have all your energy gap operators. You had Eg, tau n, you had Eg, tau n minus 1, and goes all the way to you had Eg, tau 1. So that's how this works. So just another recollection that if you have some Hamiltonian given by some H0 plus V, which is essentially some sort of coupling. So we considered this previously, where H0 was your matter system and V was essentially your light matter interaction Hamiltonian, and it essentially coupled the states of your two-level system by means of the external light field. So this was your light matter interaction Hamiltonian. I'm talking about previously, and then this was your matter system, which contains your system, your bath, and then your system bath interactions. So this is very similar to this case where Right now, you have your matter system and you have your system Hamiltonian, your Bath Hamiltonian, and your system Bath Hamiltonian. So in the previous case, your V was explicitly time dependent. Here, the system path coupling incurs time dependence as a consequence of the uh, fluctuating path coordinates, actually. So that's why its time dependence is only shown in the interaction picture, but not in the equation here. And it's a bit of a nitty gritty which can be skipped over if confused. But you consider this, and then in this case, you consider this to be the time independent part of the Hamiltonian, and then this to be some sort of perturbation. So in this case, your system path coupling essentially perturbs your electronic transition and causes and generates dynamic fluctuations in your electronic transition and is hence treated in the interaction picture. So just to draw parallels, if you consider your time evolution operator for this case, for this case in the past, which we had considered. So we write your total time evolution operator. See, I went back to the U here, but here I want to explicitly make clear that this is not your energy gap operator I've drawn here. This is your time evolution operator. Let me make it extremely clear. So if you consider your total time evolution operator with respect to H, right, we wrote it as U hat 0t and U hat I t. Let me erase this out because this is extremely interesting. So in the past, we had written your full time evolution operator as a product of two time evolution operators, where one time evolution operator was given in the interaction picture and contained the perturbation terms, and the other time evolution operator was your free propagator, or to say just propagates with respect to H0, which is here. Sorry, I should use a different color. So this is your free propagator, right? Propagator. Yes, and then so what we did was we wrote the time evolution operator as exponential minus I upon h bar, h0t, which is again your free propagator, which is u0t, and then you have a u hat it, which was written as exponential positive minus I upon h bar, then the integral from 0 to t, and then you can write v. I'm so sorry, I don't exactly recall if I used v or uh, some people also use h prime t for the same perturbation. So some people use h prime t, h1t, v of t. So I suppose I've used v of t previously, so I'm just going to continue with v of t. But if I've used something else, I apologize. So then you write it as vi tau d tau, right? And in this case, this vi tau was written in the interaction picture with respect to your matter system. So what that means is that you write e raised to the power I h0 tau over h bar, and then you had v of tau e raised to the power minus I h0 tau over h bar. So here we would still write this tau, if you recall, because this operator, right, v, this perturbation already has time dependence in the Schrodinger picture, and hence we are mentioning it in the Hamiltonian. So this, in this case, when you consider your perturbation in the interaction picture, it has time dependence due to two factors. One, because it's in the interaction picture and has time dependence due to the free propagator, which is removed here, and number two, because it itself, the operator itself, depends on time in the Schrodinger picture. So now, I hope this is a good recap of what we had studied in the past. So this is like sort of like essential quantum mechanics review, right? Now, let's use the same principle to treat the system bath coupling as a perturbation. I'm sorry if I wasn't too specific or explained this really well in the previous video, so I wanted to do a better job at it. So now if you consider your matter system, right? You write it as your system Hamiltonian and your bath Hamiltonian and your system bath coupling. And then the system bath coupling does not have any explicit time dependence before it is treated in the interaction picture. So I'm just trying to draw parallels between what we have learned and how we can apply it to our current case so that there's a better flow in understanding, right? So now if we treat this as your time independent part and then this as in your interaction picture, so we need to define what we are to be more clear, we need to define the interaction picture very clearly. So you are writing this in the interaction picture with respect to the system and the bath Hamiltonians, which we consider to be static in time, right? So then in this case, if you want, so this in this case would be something like analogous to V, which is like your perturbation, right? So in this case, we treat that as some sort of perturbation which perturbs your electronic transition essentially. And so how do you write your time propagator in this case? In this case, your time propagator of your matter system, which is given by exponential minus I upon h bar h0t, is again given by two components, which will just be exponential minus I upon h bar hs plus hbt, which can be separated out because these are two operators in two different spaces. So you can very simply write this as minus I upon h bar hst exponential minus I upon h bar hbt. And of course, after this, you have your positive time ordered exponential is given by minus I upon h bar 0 to t hsb tau t tau. And here, this hsb tau has time dependence only because of the fact that it is in the interaction picture. So hsb tau can be written as a time evolution operator with respect to hs and hb, and then you smudge it in between two of these. Let me not talk about it. Let me just write it down. So you have exponential I upon h bar hs plus hbt, and then you have hsb, which does not have any other time dependence, as contrary to the previous case where the perturbation itself depended on time in the Schrodinger picture. Right. So this is your entire case in this case for your time propagator. So that's exactly what I was trying to explain over here, but I suppose I wasn't being clear enough. So I wanted to clarify this. Now, in this case, I've written it for the full matter system, but you can consider instances of the matter system. So here I'm considering the excited state of your matter system, which contains your system Hammer propagator, your bath propagator, and then this is your system bath coupling propagator. So this is why it's written this way. And in the case of your ground state, since your system and system bath couplings are treated to be zero because we're writing the Hamiltonian of the excited state with reference to the energy of the ground state. So you treat the system and the system bath fluctuations of the ground state to be zero. And then that's why the Hamiltonian of the ground state is just the same as the Hamiltonian of the bath. And the propagator of the ground state Hamiltonian is just the time propagator of the bath. So I hope this is extremely clear now. And yep, so we can proceed with our discussions. Another important comment which I would like to make is these are forward time propagators. So essentially, they propagate your quantum system forward in time. But let us also consider your backward time propagators, right? So, how would a backward time propagator look like? It would be exponential I upon h bar times h0 t. So this would propagate your matter system forward in time by time t, and this would propagate your matter system back in time by time t. So this is the sorry. I think I messed the order up. This is a forward time propagator, so it propagates your system forward in time t, and then this is your backward time propagator. So it propagates your system from time t to, let's say, time zero. So it propagates it back in time t, right? And then in this case, this can be written as exponential I upon h bar hs plus hbt, and then you have a negative time ordered exponential in this case, which would be 0 to t hsb tau d tau. So this negative time ordered exponential, to remind you guys, has the following structure. So 0 to t hsb tau d tau can be written as the identity operator plus sum over n from 1 to infinity. You have minus I upon h bar to the power. So you have positive in this case. Plus I upon h bar to the power n. So that just comes from here. So you have positive I upon h bar to the power n. And then you have the n-fold integral 0 to t tau n, 0 to tau n, t tau n minus 1, so on and so forth, to 0 to tau 2, t tau 1. But in this case, the order of the operators is reversed. I would just like to clarify that here I wrote it in terms of the energy gap operator of the excited state, but here I accidentally, not accidentally, but I was trying to discuss from a more general context. So I wrote it as the system bath operator, which is, so this system bath operator for a two-level system would just correspond to the fluctuation in transition energy of the excited state. But let me not do that just to maintain consistency. Let me write it as u hat eg tau, just to maintain consistency with the positive time ordered exponential I'd written above. But yeah, so this system bath coupling will be different in the case of other systems which are not two level systems. But for now, let me just use this, and you get u hat eg tau 1, u hat eg tau 2, so on and so forth to u hat eg tau n. So the order is reversed. So the operator which is supposed to act later in time acts earlier in time first, or acts first, and then the operator which is supposed to act first acts later on if it is acting on the system from this side. But this negative time ordered exponential generally acts on the bra, or the complex conjugate of the state vector on the system. So that's why it acts from this side, and that's why these negative time ordered exponentials are defined this way. They're not defined this way, but the mathematical structure is this way. So without further digressions, I hope this is clear. And then this is a backward time propagator. And we had discussed this previously when we were considering the the case where we were initially deriving our third order nonlinear response functions, where we had considered a full Hamiltonian to be our matter system as well as its perturbation. So when we had considered this at the beginning of our lecture series, we had we had talked about this. I wouldn't say derive, but yeah. So it's again composed of two components. One component being your time propagator with respect to your system and path, and one component being your time propagator with respect to your system path coupling. I just realized something right now. I have made a mistake in the ordering of these two terms because it's quite evident that if you consider your forward time propagator, where have I written that? Okay, so if you consider your forward time propagator, you have this, which is essentially your time evolution with respect to your system and path, and then you have the time propagator for your system path coupling. So to derive your backward time propagator, I take a Hermitian conjugate of my forward time propagator, right? And when I take a Hermitian conjugate of two operators A and B, it would be B dagger, A dagger, and not A dagger, B dagger. So what I'm trying to say, and I apologize for the mistake, would be that for your backward time propagator, you better write your time ordered, negative time ordered exponential first, right? And then followed by your propagators with respect to your system and path. I apologize for the mistake. Right. So what I was trying to say here is, just to finalize our thought, was if you have exponential minus I upon h bar h0t, and you take a Hermitian conjugate of this, so you derive your backward time propagator, and this one is defined, or we derived it to be minus I upon h bar hs plus hbt, and then a positive time ordered exponential from 0 to t of the system path coupling Hamiltonian. If you take a Hermitian conjugate of this, you derive your backward time propagator. And so when you take a Hermitian conjugate of this, as you recall, AB dagger is B dagger, A dagger. So the order has to be reversed. This term will come first and then this. So the Hermitian conjugate of the positive time ordered exponential would just be the negative time ordered exponential, which is this term. And then you have the Hermitian conjugate of the time propagator with respect to the system and path Hamiltonians, which is given here. And when you take the Hermitian conjugate, you get this term. So this checks out. So we constructed the backward time propagator as well as the forward time propagator with respect to the complete matter system. So the backward time propagator will also be quite important. So that's good. So we had to conclude all these discussions to this point, and I hope they are clear. So now we can go right ahead into deriving your response function expressions. And as you recall from our previous class, we had R1 to R4, which, if we go all the way up, are embedded within the mathematical structure of your third order nonlinear response function. And R1 and R2 generally correspond to stimulated emission processes, and R3 and R4 generally correspond to bleach processes for this simple two-level system. So your R1, I'm going to drop this 3 from now, so I'm just going to write R1, R2, R3, R4, and it's well known that they are third order nonlinear response functions. And I will also drop the function of T1, T2, T3. So I won't refer to these anymore because it's just very tedious to write down. And then, so R1 is this, T1 plus T2 plus T3, and you have a mu 0. and then you take an equilibrium expectation value or equilibrium ensemble average of this 4-point dipole correlation function. So we calculate this. Let's start off with calculating R1. Then we calculate R2, R3, and R4 similarly. Just to recall, just to remind you one last time, we're calculating it for the simple two-level system. So you can write this as a trace with respect to the equilibrium ground state, essentially your equilibrium density operator. We'll talk more about that. So you have mu t1, your 4-point dipole correlation function, traced with your equilibrium density operator t1 plus t2 plus t3. You have mu 0, and you have rho 0, which is your equilibrium density operator, which we sometimes write as rho equilibrium. And then, as I previously discussed, this trace can be broken down into a trace over your path and then a trace over your system. So you first perform a trace over your system states, and then you can perform the trace of the resultant expression over the path states, because the dipole operators are only functions of your system states and are independent of the path under the Born-Oppenheimer approximation. And your dipole operators being independent of the path. So this is, let's just say, some path coordinate. So your dipole operators being independent of that is known as your Condon approximation. So here we applied the Condon approximation, which comes from the Born-Oppenheimer approximation, but this is known as the Condon approximation. And using the Condon approximation, we first take a trace over your system states, because the dipole operators only act on your system states, and then you compute the trace of the resultant expression. So let's compute the trace over the system states first with the system equilibrium density operator, which would be this, and then this is your path equilibrium density operator. So you have mu t1, mu t1 plus t2, mu t1 plus t2 plus t3, mu 0, and then your system equilibrium density operator, which we treat to be G, if you recall, because your system is in your ground state, and this holds very good for electronic spectroscopy essentially. So this is equal to, you're taking a trace over your system states, so you're taking a trace over G and E, and the contribution from the E term is 0, as G and E are orthogonal to each other. So this boils down to this term, mu t1 plus t2, mu t1 plus t2 plus t3, and mu 0, get G. So now we write this in terms of the time propagators. So you have to write it as exponential I upon h bar h0 t1, and then you have mu, and then you have exponential minus I upon h bar h0 t1, and then from this case you will have exponential I upon h bar times h0 t1 plus t2, then you have mu, and then you have exponential minus I upon h bar h0 t1 plus t2, and then lastly for this term you have exponential I upon h bar h0 t1 plus t2 plus t3 mu exponential minus I upon h bar h0 t1 plus T2 plus T3. So you have these three terms. Now let's consider the terms in this cap first. So the terms in this cap are this term and this term. So this term corresponds to a forward propagator of time t1, and this term corresponds to a backward propagator of time t1 plus t2. So equivalently, if you look at the maths too, it just corresponds to a backward propagator of time t2. So what I mean to say is here what you end up getting is just exponential I upon h bar h0 t2, which can be seen very clearly. So this a way to think about this logically is that this propagates your system backward in time over t1 plus t2, and then this propagates your system forward in time over t1. So essentially what you're doing is you're just propagating your system back over t2. Right. Now let's consider the terms in this gap um, over here. So if you consider the terms in this gap, you are considering this term and then this term. So this term corresponds to a forward propagator over t1 plus t2, and this term corresponds to a backward propagator over t1 plus t2 plus t3. So essentially what this means is that the uh, the propagator would be exponential. The resultant propagator would be IH0 T3, or a backward propagator over time T3. So that's what these mean physically. And of course, you have this term over here, which we have to consider, right? So you get G, you have your first term here, e raised to the power I over h bar, h0, t1. And then after that, you have a backward propagator, h0, t2, and then you have a mu, and then you have a backward propagator, h0, t3, and then you have a mu, and then you have a forward propagator over t1 plus t2 plus t3. Right. I hope that's, and then you have another mu. So you have your four dipoles here. And then mu acting on ket G will, okay, I'm sorry, I should have defined the dipole operator structure too, but we've defined it far too many times. But for your two-level system shown over here, your dipole operator comprises of two off-diagonal terms, which means that your dipole operator looks like this: mu eg get e bra g plus mu ge get g bra e. So what this does is it goes from a ground state and projects it onto an excited state e. So your expression looks like this: mu eg, and then you have this term acting on get e. So you have e raised to the power minus I over h bar, h0 acting on small the excited state e. Now h0 comprises of your system component, path component, as well as your system path interaction. So just recall that the resultant expression has to be traced over your path states as well. So in this case, it's just that we would write this as e raised power minus I upon h bar, h capital E, t1 plus t2 plus t3, which means that it's the Hamiltonian of the excited state. Because right now, we can just consider h small e, which would be the most logical thing to do, but just note that the resultant expression has to be traced over your path states, and that includes your system path fluctuations as well. So if the mathematical nuances here are not too clear, just know that I'm writing the capital E here because I need to consider the fluctuation in transition frequency of the excited electronic state when I do the trace over the path. So right now I'm just doing the trace over the system states, right? So next, this dipole operator mu acts on get E and brings it back to the ground state, which would be mu GE. And now you're in the ground state, get G. And then this backward time propagator over T3 acts on it. So you get E raised to the power I upon H bar H G T3. Then you have mu, which acts on get G. And then what you get is mu EG again. And then you are in the excited state E. And then you have this backward time propagator over T2, which acts on it. So you get E raised by I upon H bar H E T2. Then this dipole operator acts on get E and brings it back to the ground state. And since mu EG and mu GE are just complex conjugates of each other because the dipole operator is Hermitian, I just write to the power 4, and then you're back to the ground state, and then you have this final backward time propagator over T1, so that gives you E raised to power I upon H bar H G T1. And now this expression which we have just calculated has to be traced with respect to the bath, and you have your bath equilibrium density operator. So essentially it's equivalent to mu Eg to the power 4. And before I write it in the interaction picture and pull out the coherence terms out and so on and so forth, I can write it like this: E raised to power I upon H bar HGT1, E raised to power I upon H bar HET2, E raised to power I upon H bar HGT3, E raised to power minus I upon H bar HE T1 plus T2 plus T3, and then this is a bath equilibrium average because it's a trace over all your bath states with your bath equilibrium density operator. So things are looking good as of now. And now we can put in the forms of the time propagator and time reversal operators as we had previously discussed. So this would just be H B, right? And then this would contain two terms. So you have E raised to power I omega EG T2, and then E raised to the power I upon H bar H T T2. And then, of course, you have your negative time ordered exponential I upon H bar from 0 to T2 in this case, right? And you have d tau and you had Eg tau. I hope that's clear. And then in this case, this Hg will just be Hp. And then this term, where you have e raised to power minus I omega Eg T1 plus T2 plus T3 e raised to the power I upon H bar Hb T1 plus T2 plus T3. And of course, you have exponential positive minus I upon H bar 0 to T1 plus T2 plus T3. You had Eg tau d tau, right? Now let's do some mathematical cancellation. So this plus I omega Eg T2 will cancel this, and you are left with this u Eg to the power 4 e raised to power minus I omega Eg T1 plus T3, and within the bath equilibrium average is left the following terms: e raised to power I Hp T1 upon H bar, of course. Then from your second term, you have okay, I'm sorry, I made that mistake again. So these two terms should have actually come after this. I apologize for the mistake because they are backward time propagators, and I had shown about that it should come after this. But since these coherences are just scalars, there's nothing to worry about. But this term should actually come after this, right? So I hope that's clear. And then um, you have the time propagator, exponential negative I upon h bar, 0 to t2 t tau. You had eg tau, and then you have this term, which is e raised power I upon h bar, hb t2. I should just be writing it as ihb t2 upon h bar. And you have your third term, which is just e raised power I h b t3 upon h bar. And then lastly, you have e raised to the power I. Sorry, it should be a minus. Sorry for the mistakes. Minus I upon h bar hb t1 plus t2 plus t3. And then you have your positive time ordered exponential. I hope this is clear. And then you take a trace. Maybe I should just go back to the trace notation of with the Bath equilibrium density operator. So at this point, some cancellations are quite obvious and evident. So let's do those first. You can cancel this, and the T2 plus T3 term. So what is left out is a trace over all the path states of e raised power I h p t1 upon h bar. The negative time ordered exponential 0 to t2 d tau. You had eg tau, and then you have a time propagator with respect to the Bath Hamiltonian, and then you have the positive time ordered exponential 0 t1 plus t2 plus t3. You had eg tau t tau, and then you have your path equilibrium density operator. Yes. So we need to deal with this term quite carefully, and from first intuition as well, you can see that if this is some arbitrary operator, call it alpha, and then you have e raised power plus I h t1 over h bar and e raised power minus I h t1 over h bar on either side of it. You're essentially, what you're doing is you're evolving that operator, or transforming that operator, or translating that operator over t1. So in this case, you're translating that operator with respect to the path over t1. Quite obvious. So what that essentially means is that your negative time ordered exponential is acting over the period t2, but these two operators on the left and the right, they traverse it forward in time by t1, and then it acts over the duration t2. So I will explain this in better detail, but what that essentially means is that this negative time ordered exponential needs to be integrated, or the duration over which the series needs to be expanded is between t1 and t1 plus t2. T tau, you had eg tau, and then you have your positive time ordered exponential 0 to t1 plus t2 plus t3 again. T tau, which is the variable of integration, and then you have eg tau with the Bath equilibrium density operator, which again can be recast as the equilibrium Bath expectation value of the product of these two time ordered integrals. t1, t1 plus t2, uh, d tau, you had eg tau. I apologize for moving this infinitesimal d tau towards the left and right constantly, but yeah, that doesn't make a difference. Then integrated from 0 to t1 plus t2 plus t3, you had eg tau. Let me just leave it towards the left this time, d tau. And then this is a Bath equilibrium expectation value. And this was called F1, let us call it F1, or the dephasing function corresponding to the R1 response function. So R1 can be written as mu Eg to the power 4, where mu Eg square from your linear absorption spectroscopy experiment, or as we discussed the linear response theory from the previous lecture, is known as your oscillator strength. So this quantity is very specifically defined as your oscillator strength. So this is the square of your oscillator strength. You have the coherence term, which is non-rephasing in this case, because the phase acquired by the signal over T1 is not cancelled by the phase acquired over T3. In fact, they sum each other up. So that's why they're known as non-rephasing response functions, because there's no reacquisition of phase in this case, times F1. And then this F1 is just your dephasing function, or uh, it encodes information on your spectral line shape. And then this F1 is a product of two time ordered exponentials. So the first one is a negative time ordered exponential. So this acts on the bra of the Bath equilibrium density operator, quite obviously. And then the other is a positive time ordered exponential. So it acts on the ket of the Bath equilibrium density operator. I will show you guys a shortcut on how the response function's dephasing function can be written by directly looking at the Feynman diagrams, but for now, let's stick to the full blown procedure. Okay, so this is R1, and within R1 is F1, which corresponds to the dephasing function of R1. Yes. So we are at this point now, and we should go back and understand what happens at this point. So, digression. So you have I over h bar hp t1. So this is a time reversal operator over t1, and then you have this negative time ordered exponential from 0 to t2. You had eg tau t tau. So this integration variable tau belongs somewhere between 0 and t2. Okay, and then you have a time propagator with respect to the Bath Hamiltonian, and it propagates over t1, propagates your system over t1. So now the way you think about this, as I previously described, is this is just some arbitrary operator, and then it is this operator is evolved in time over t1. So if you have a time reversal operator times some operator times a time propagator, that gives you the overall operator being propagated by that time, as we had previously discussed. So please don't get confused by this energy gap operator, because in the energy gap operator we always use this UEG. But if I write this as U hat, which is a time reversal operator, so if you call it U hat minus T1, or to be more generic with the notation we were using previously, you had dagger t1, which is a time reversal operator, and then this is a time propagator. Sorry, you had t1 with respect to the path. So I put a b at the bottom, right? So what you're essentially doing is if you act an operator on this, so you had b dagger t1. Sorry, what I meant is if an operator is smudged between the two, so let's just call that arbitrary operator a hat, and you had b t1, and this a hat, just assume it to depend only on the path. So forget about the rest. So to avoid confusion, so you get a hat t1, or I can just put a b at the bottom. So this is propagated with respect to the path by time t1, and this is what we have discussed in fundamental quantum mechanics. So essentially, what that means is that if you have this operator alpha, what you're doing is you're propagating this alpha by time t1. And within this UEG tau, as we had previously discussed, that these energy gap operators incur time dependence only in the interaction picture, and the interaction picture is with respect to the system and path Hamiltonians. So you can write it as e raised to the power I hs plus hp tau upon h bar UEG times e raised to the power minus I hs plus hb tau upon h bar. So that would be e raised to the power I omega eg tau, e raised to the power I hp tau upon h bar UEG, and then the other terms g tau, and then e raised to the power minus I hp tau upon h bar, and then these two are just scalars, so they will cancel each other out, and then you have this. So essentially, if you think about it, your energy gap operator has these two terms, ihp tau and ihp minus tau on either side. So if you act I exponential ihp t1 upon h bar and minus ihp t1 upon h bar, what you effectively get is a negative time ordered exponential from 0 to t2 of e raised to the power ihp t1 plus tau upon h bar mu eg e raised to the power minus ihp t1 plus tau upon h bar, and of course you have your d tau. So what that effectively means is that this energy gap operator is being propagated by time t1 plus tau. So this full thing is just you had eg t1 plus tau, and what that gives you is a negative time ordered exponential from 0 to t2 of you had eg t1 plus tau t tau. So you can just make a integration variable substitution, which is very simple. So just replace tau prime by t1 plus tau, and then just replace tau prime again by tau. So just take tau prime as t1 plus tau, change the variables of integration, then just replace tau prime by tau, right? Because it's just a variable of integration. And what you get is a negative time ordered exponential from t1 to t1 plus t2 of u hat eg tau t tau. So these two integrals are just equivalent, quite obviously. So this is how you mathematically and rigorously prove that your term, which is given here, this term which I have, not this term which I've denoted by alpha, but essentially this entire thing highlighted in yellow, this full term is simply equivalent to the negative time ordered exponential from t1 to t1 plus t2. Yeah, so that's mathematically more accurate. And yeah, so this is how you prove it mathematically too. So the entire idea is that you have a time propagator over T1 and sorry, I should not say time propagator, but a time reversal operator over T1 and a time propagator over T1. And when an operator is smudged between this time reversal and time propagator, it essentially you're just evolving that operator over T1. And when you evolve that operator over T1 and you consider the time ordered integrals and this and that, um, it's quite easy to think of your negative time ordered exponential acting over the duration t1 to t1 plus t2. Yes, so in the end, that's how your dephasing function comes about. So this is the story for R1, and likewise, we can do the same for R2, R3, and R4. So now let us consider R2. And I have the expression with me for R2, which is just mu 0, mu t1 plus t2, mu t1 plus t2 plus t3, mu t1, and then this is an equilibrium ensemble average with respect to the bath and the system, the complete thing. And again, in this case, we take a trace over all your system states first, and then the resultant expression is traced over all your path states. Again, we can consider the various caps in the expression. Here, it's quite simple. Here, you will have a contributor from e raised to the power minus I h0, which is your matter Hamiltonian, t1 plus t2 upon h bar, and then you'll have e raised by I h0, t1 plus t2 plus t3 upon h bar, and then as we discussed, this is a time reversal operator, and then this is a time propagator. So in the end, the effective operator is just a time reversal operator over t3, or the math just dictates that if you don't believe the argument. And then you have this gap here where you have a time propagator over t1 plus t2 plus t3, and you have a time reversal operator over t1. So you effectively get a time propagator over t2 plus t3. Sorry for the mistake. Yeah. So we can write R2 as a trace over the path. And then you have a trace over all your system states. You have mu, and then you have effectively e raised power minus I h0 t1 plus positive, sorry, and that comes from here. You have another dipole operator, and then after that you effectively have a time reversal operator over t3, time t3, so it reverses the system or propagates backward over t3. Then you have another dipole operator, and now you have the time propagator over t1 and t2, and then you have the dipole operator, and then you have a time propagator over t1. Yes, that comes from the time propagator comes from here. And then you have your last dipole operator along with the system equilibrium density operator, and then you have the next trace to be performed over the bath equilibrium density operator. So now we worry about this system trace first. So we pull this down, and as the argument we have made previously, but we just continue with that, where your system density operator is confined to this element Gg. So your system is assumed to be in the ground state prior to any light field perturbations. And when you take a trace over the ground state and the excited state, the only term that survives is the ground state one. So you have bra g mu e raised to power I h0 t1 plus t2 upon h bar mu e raised to power I h0 t3 upon h bar mu e raised to power minus I h0 t1 plus t2 upon h bar mu e raised to power minus I h0 t1 upon h bar mu acting on get g. So this is what it effectively boils down to, and then we recall the structure of the dipole operator. So mu acting on get g gives you mu eg, and then you have a get e here, and then you have a time propagator over t1 which yields e raised to power minus I h e t1 over h bar, and then this dipole operator acts on get E and brings it back to the ground state. So you get mu GE. So now you're back to the ground state, and then you propagate over the ground state over T1 plus T2. So you get e raised to power minus IHG T1 plus T2 upon H bar. And then after that, the dipole operator acts on get G and takes it to get E. So you get mu EG square, and then you have get G here. And then you have a time reversal operator over G over time T3. So you get e raised to the power IHG T3 upon H bar. And then mu acts on get G. Mu acts on get G and takes it to 1, 2, 3. Okay, I have an extra dipole operator. I don't know why. H0, T1 plus T2. So you have 1, 2, 3. Okay, I don't know why I have an extra dipole operator. H0, mu. Then you have this. Then you have mu. This. Then you have mu. Okay. And then this. Okay, sorry. This term was extra here. I apologize for the mistake. So we're just gonna contain this term. And then, yep, so this is an extra term. So we're just acting on get G here. Okay, so we'll have to do the computation again. I apologize for the mistake. Quite obviously, I'm not gonna do it too carefully. I'm just gonna write mu eg to the power 4. You can already see it coming. So let's not worry about that. So you have a time translation or a time propagator over the ground state over time t1. So you get e raised to power I hg t1 upon h bar. Mu projects it from the ground state to the excited state. So you get the first contribution towards mu eg. Then after that you have this second term which is a time propagator over the excited state over time t1 plus t2. So you get e raised to power minus I h e t1 plus t2 upon h bar. Then you have mu which brings it back to the ground state, and then You have a time reversal operator over time t3 which acts on the ground state, and then you have the dipole operator which projects it back to the excited state. So this is the third contribution towards the mu eg to the power 4 term. And then you have the propagator, sorry, the time reversal operator over the excited state over time t1 plus t2, which gives you e raised to power I h e t1 plus t2 over h bar. And then this brings it back to the ground state, and then you take a trace, and then and then you just have bra g get g. So yeah, they cancel out, and then you have the resultant expression is traced over the path states with the path equal. Okay, so you do this, and then you have to compute this expression, and then again you write the excited state Hamiltonians in the system path picture, and the ground state Hamiltonians can just be replaced by HB, and then these excited state Hamiltonians can be written as follows. You have mu Eg to the power 4, trace over the path, then you have e raised to the power uh, I omega Eg t1 plus t2, and then oops, I should reverse the order. I should be really careful this time. In this case, you will have a negative time ordered exponential from t1 to t2. You had eg tau, t tau, and then you have e raised to power I omega eg t1 plus t2 e raised to power I hb t1 plus t2 upon h bar. Then the next term will just be e raised to the power I hb t3 upon h bar. Then from the next term you have e raised to power minus I omega eg t1 plus t2, and then you have e raised to power minus I hb t1 plus t2 upon h bar. And then you have the positive time ordered exponential from 0 to t1 plus t2. You had g tau, t tau, and then you have e raised to power I h p t1 upon h bar, and you have the path equilibrium density operator. So here we have some cancellations which are quite evident again. Um, 1 second. I think I have made a mistake again. IH0 t1 plus t2 e raised to the power minus IH positive IH0 t1 plus t2. So your coherence is fully cancelled out, which doesn't. Oh no, oh no, oh no. It's t2 plus t3 here. I apologize. Huh. Okay. So we will have to change this. T2 plus T3. Then this becomes T2 plus T3. And likewise, this will become T2 plus T3. And yep, then this becomes T2 plus T3. And then this is an integral over T2 plus T3. And then this would be T2 plus T3. That makes sense. Then this cancels this, and then you have your coherence terms coming from here. Your HB T2 plus T3 term cancels here. And then you have IHB T1 upon H bar, which is analogous to your previous case. And of course, the path density operator is a function of the path Hamiltonian itself, right? So you write this as for the canonical ensemble, you write it as e raised to the power minus beta hb upon trace e raised to power minus beta hp as I had previously described. So this is an operator of the path Hamiltonian and this is an operator of the path Hamiltonian, so they commute with each other. So I shall take this from here all the way to here, and then the case becomes analogous to the previous one. So you have mu eg to the power 4, and then I commute this to the other side. So you have trace over path, uh, time reversal operator with over t1, some operator, and then a time propagator over t1. So the structure would be very similar to what we have discussed already. And sorry, one moment. I think there's a typo somewhere which I have made again. Okay, great. This has a negative sign here, and then this has a negative sign. So that's good. So in a sense, our work is a little bit simpler this time. We don't need to do what I just discussed, because I can let me just show you the math. So you take a trace over the path. You have this negative time ordered exponential from 0 to t1 plus t2. You had eg tau t tau, and you have this one term that survives. So you have e raised to the power, which makes sense because this is a rephasing process. So our coherence terms look good. And you have this e raised to the power I h b t1 upon h bar. And then you have this positive time ordered exponential from 0 to t2 plus t3. You had eg tau d tau. And then you have this negative this time propagator with respect to the path over t1. Then you have this. So again, as the previous case we discussed, this positive time ordered exponential can just be written as this minus I1 h bar from t1 to t1 plus t2 plus t3. So essentially, you're propagating this operator over t1. So the duration over which it acts is from t1 to t1 plus t2 plus t3. So I hope that's clear. But you can work the math out for clarity by writing mu eg tau as e raised power I h p tau upon h bar u eg e raised power minus I h p tau upon h bar, and then bring both of these inside and then do the substitution and so on and so forth, and you get the same result. So R2 is equal to u eg to the power 4 exponential minus I omega eg t3 minus t1, and the dephasing function f2, which I shall write now as an equilibrium ensemble average, equilibrium path ensemble average. So it's a product of a negative time ordered exponential with a positive time ordered exponential. The negative time ordered exponential acts over t1 plus t2. And then you have a positive time ordered exponential which acts from t1 to t1 plus t2 plus t3. The integration is performed over that time, and it is an equilibrium ensemble average with respect to the path states. And then this would be called your dephasing function f2. Now, likewise, let's quickly derive R3, which in its 4-point dipole correlation function looks like this: mu0, mu t1, mu t1 plus t2 plus t3 and mu t1 plus t2 equilibrium. And I'm just going to go ahead and write the expression down this time without explaining much. So you take a trace over the path states, trace over the system states. You have mu e raised to the power I h0 t1 upon h bar. Then you have mu. Then you have e raised to the power I h0 t2 plus t3 upon h bar. You have mu, and then you have e raised to the power minus I h0 t3 upon h bar. Then you have mu, and then you have e raised to the power minus I h0 t1 plus t2 upon h bar. You can work the math out slowly just to verify this. And this is how this expression would look like. You compute the trace over the system states first, and you effectively get this expression e raised to the power I h0 t1 upon h bar mu e raised to the power I h0 t2 plus t3 upon h bar mu e raised to the power minus I h0 t3 upon h bar. Then you have your final dipole operator and then a time propagator with respect to the matter Hamiltonian over t1 plus t2 acting on get g. And then you work the math out where you have your four dipole operators which act on the ground state and project it to the excited state and vice versa. So you get mu eg to the power 4, and then you get this trace over the path states of e raised to power I h e t1 upon h bar e raised to power I h g t2 plus t3 upon h bar e raised to the power minus I h e of t3 upon h bar and e raised to power minus I h g of t1 plus t2 upon h bar with the bath equilibrium density operator. And then this gives us mu eg to the power 4 trace over the bath. The first term can be written as e raised by I omega eg t1. Again, sorry, please be careful with the ordering. The negative time ordered exponential will come first. The integral from 0 to t1 of u hat eg tau t tau. Now the system and bath components will come, so you get e raised to power I omega eg t1, e raised to power I h b t1 upon h bar. Then the second component comes in where you have e raised to power I h b t2 plus t3 upon h bar. Then the third one where you have e raised to power minus I omega eg t3, e raised to power minus I h b t3 upon h bar. Then you have a positive time ordered exponential where this is integrated from 0 to t3. U hat eg tau d tau. And then, of course, you have the e raised to the power minus I h b t1 plus t2 upon h bar acting on the bath equilibrium density operator. Now, in this case, are there any cancellations as such? Yes, there's one where this term will just cancel this out. So you get mu g to the power 4. Of course, these are your coherence terms, which are correct because R3 also corresponds to a rephasing process. It's your rephasing ground state bleach. Right. Now, you have e raised to power I h p t1 plus t2 upon h bar on the left, some operator, and then e raised to power minus I h p t1 plus t2 upon h bar on the right. So you're propagating that operator with respect to the path Hamiltonian over t1 plus t2, and using the math which we had previously described, you just have to change this from 0 to t1 plus t2, and then this to t1 plus t2 plus t3. So it's just the math, and you write it as an equilibrium ensemble average with respect to the path states. So again, a product of a negative time ordered exponential with a positive time ordered exponential. So you had Eg tau t tau and a positive time ordered exponential minus I upon h bar from t1 to t2 to t1 plus t2 plus t3 u Eg tau t tau was the path. Lastly, we derive R4, whose dipole, 4-point dipole correlation function looks like this. Again, this is F3, your dephasing function corresponding to R3. We will summarize everything out and look at a short form method in which you can also write these dephasing functions out towards the end of this lecture. So you have mu t1 plus t2, mu t1 and mu 0, which makes sense because in R4, all the interactions of the light field with the matter system are from the ket side. So all the light fields interact with the ket side of the density operator. So the ordering within the equilibrium expectation or ensemble average is 0, then T1, then T1 plus T2, then T1 plus T2 plus T3 from the right to the left, right? So you take a trace over your path states, and then you take a trace over your system states of this 4 dipole operators, and you have your system equilibrium density operator, and then you have your path equilibrium density operator here. And again, let us evaluate the system part first, and then we take a trace of the resultant expression with the path equilibrium path density operator, and then you take a trace of all of that with the path states, right? So again, this gives you the expression where you have Raji towards the left, because you assume that the equilibrium system density operator is just comprised of this element, right? So you get e raised to power I h0 t1 plus t2 plus t3 upon h bar. You have a mu, and then you have a time propagator over t3. Please work the math out carefully if you're confused. Then you have a time propagator over t2, and then you have your time propagator over t1, and then you have your last dipole operator acting on get g, right? So this gives you mu eg to the power of 4, and I will directly write the trace over the path states. So trace over the path states, and you get e raised to the power I h. So this would take it to this would be e, then this would be g, then this would be e, and then this would correspond to g. So I h g t1 plus t2 plus t3 upon h bar e raised to power minus I h e t3 upon h bar e raised to power minus I h g t2 upon h bar and e raised to power minus I h e t1 upon h bar with the path equilibrium density operator. And then again, hg is just, let me change pen color. Hg is just the path Hamiltonian. He is written using the positive and negative time ordered exponentials. In this case, it would just be positive time ordered exponentials. So you get mu eg to the power 4, trace over path. You have e raised to power I h p t1 plus t2 plus t3 upon h bar e raised to power minus I omega eg t3 e raised to power minus I h p t3 upon h bar, and then you have the positive time ordered exponential from 0 to t3 of u e g tau d tau. Then you have the following term e raised to power minus I h p t2 upon h bar, and then lastly e raised to power minus I omega eg t1 upon h bar, e raised to power minus I h p t1 upon h bar, and positive time ordered exponential minus I upon h bar from 0 to t1 of you had eg tau t tau bath equilibrium density operator, and then the trace over all the bath states. So these two terms correspond to the coherences. And do we have any cancellations? Yes, we do. We have this term cancelling with this. And I shall not talk this time. I'm hoping that e raised to power I hp t1 plus t2 upon h bar, some operator times e raised to power minus I hp t1 plus t2 upon h bar is very obvious to you what I'm going to do. So I'm just going to write this as mu eg to the power 4 times e raised to power minus I omega eg t1 plus t3, which makes sense because this is a non-rephasing ground state bleach process, times the equilibrium bath ensemble average or expectation value of two positive time ordered exponentials from t1 plus t2 to t1 plus t2 plus t3, and from 0 to t1. Equilibrium ensemble average with respect to the bath. Yes. So this is your dephasing function f4, and this is r4. So we have successfully derived r1, r2, r3, and r4 to the point where we have our dephasing functions. Now, once we have these dephasing functions, we can derive exact analytical expressions. I wouldn't say exact because it's approximated by second order cumulant expansion, but we can derive complete analytical expressions. So before we conclude this class, let us summarize R1 through R4 and their dephasing functions, and let us do so using a shortcut method. So this shortcut method might help you construct the dephasing functions much faster for other systems which do not pertain or do not correspond to these two-level systems, and hence should be a useful tool for future calculations. So let's go back to R1. R1 for our two-level system was GG, going to EG, EE, EG, and then the emission of your signal. So these were interactions with the pass side, and the first interaction is with the get side. So this is how it looks like. So the way you construct R1, quite obviously you have mu Eg to the power 4 because all the four interactions of the light field with the density operator elements, or the three interactions of the light field and the emission of the signal field, involves projections from state G to state E or from state E to state G. Hence, you would have a dipole operator element which scales with the fourth power. And then after that, you have a coherence term which goes as such minus I omega Eg t1 plus t3. So the easy way to look at this is you write e raised to power minus I omega, the time over which it is propagated, and omega, the energy, let me not say omega, but it's the energy of the left element minus the energy of the right element's state. So, of course, scaled down by h bar. So it's just this coherence can be read as e raised to the power minus I e minus eg over t1 divided by h bar, so which contributes to this first term. So that's how you can read these double-sided Feynman diagrams. It's just the difference of the energies of the left state and the right state scaled down by h bar, and there's a minus I here. So just you can devise your own convention to quickly write down the coherences for any sort of double-sided Feynman diagram, but that's what I do generally. And then after that, you have your dephasing function. So it's quite obvious to see that there's two dephasing contributions. Firstly, towards the bra side, you have a dephasing over uh, t1 plus t2. So you write the negative time ordered exponential since it's on the bra side. So from t1 to t1 plus t2, mu, e.g. tau, t tau, and then the other element would be a positive time ordered exponential from the ket side. And that would be over t1 plus t2 plus t3. So you have mu, e.g. tau, t tau. An easy way to think about this would be to think about it in the trace form. So let's say you take a trace over your bath states, you have your equilibrium bath density operator in the center, and from the when you think about the equilibrium bath density operator, you measure the fluctuations on the ket side over t1 plus t2 plus t3 from 0 to t1 plus t2 plus t3 of mu, e.g. tau, d tau. And on the bra side, you have the negative time ordered exponential from t1 to t1 plus t2 of mu, e.g. tau, d tau. And what I have done in the expression above is just simply shift this term to the left. So that's how you can write these dephasing functions, where you write the dephasing over the bra side first and then the dephasing over the ket side. But please be careful about the ordering of terms. So you can always go down to the trace over the bath notation, place your bath equilibrium density operator in the center, and then write your positive negative time ordered exponentials on the left and right, and be careful of the ordering. So likewise, using the methods that I've just described to you, let me quickly summarize R2. So R2 would involve GG, then first interaction with the bra side, second interaction with the ket side, then bra side, and the emission of the signal field. So R2 using the method I just described would be mu Eg to the power 4, then e raised to power minus I omega Eg, T3 minus T1, because this term would oscillate at exponential, like using the method I previously told you, minus I times the energy of the leftmost element, which would be Eg, energy of the rightmost element, T1 upon h bar. So this Eg minus Ee upon h bar is just omega Ge, which is equivalent to minus omega Eg. So this term becomes e raised to power positive I omega Eg T1, which is written here. So these terms of the form Ge just has a positive contribution, right? So and then you write your dephasing function. As I mentioned, you would write your bra side dephasing first. In this case, it's very simple because you have only one negative time ordered exponential, one positive time ordered exponential. But if you consider systems which are larger than two-level systems, please be careful on the ordering of the negative and positive time ordered exponentials on the left and right side. So you get a negative time ordered exponential, and in this case, it would be from 0 to t1 plus t2 of u, e.g. tau, t tau, and a positive time ordered exponential from t1 to t1 plus t2 plus t3 u, e.g. tau, t tau. Of course, this is an equilibrium bath ensemble average, and likewise we do the same for R3 and R4. So R3 is your rephasing bleach process. So it looks something like this. So for R3, your coherences and your oscillator strength squared. And what it's trying to say is your coherences would be exactly identical to R2. Because in R2, your first coherence is GE, and then second coherence is EG, and that's the same in R3 as well. So you get e raised to power minus I omega EG, T3 minus T1. Then you write the dephasing. First, the bra side, so you get the negative time ordered exponential from 0 to T1, mu Eg, tau d tau. And then you have the positive time ordered exponential from T1 plus T2 to T1 plus T2 plus T3 mu Eg, tau d tau u Eg. And then this is the path expectation value or ensemble average. Lastly, R4. So you have GG, all interactions from the ket side, as previously described. You go back to GG, and then you have the emission of the signal field. So R4 is just u Eg to the power 4, e raised to power minus I omega Eg, T1 plus T3. So R4's coherence will exactly correspond to that of R1 because the first coherence and the second coherence is Eg, and that's the same in the case of R1. So then you have your dephasing. In this case, it's both positive time ordered exponential. So please pay careful order to the ordering, attention to the ordering. So first, if you have your, you can trace over the path, and then you have your path equilibrium density operator, and both your terms are acting from the left in this case. So the first integral would be from 0 to T1, and then the second integral would be the one from T1 plus T2 to T1 plus T2 plus T3, right? So please be careful about the ordering. That's exactly what I meant. So I delete this, and I write the two positive time ordered exponentials. This one would be from T1 plus T2 to T1 plus T2 plus T3. And then the next one would be from 0 to T1. So I hope R1 to R4 and the corresponding dephasing functions F1, F2, F3, and F4 are clear. In the next class, we will derive F1, F2, F3, and F4 further under the second cumulant approximation. And I hope there's no mathematical mistakes here. I apologize if there are any, but you can go ahead and confirm the expressions derived using the shortcut method as well as the long cut method, and then it would be a good assurance check for you guys. So in the next video, we derive these dephasing functions under the second cumulant approximation. So we'll stop here for now. Thank you so much.